Hello, this is lab number 4, week 4. And today we are going to be experimenting with a water balloon and a balloon with air in it. So then we're going to see what happens when we get a flame provided here onto one of these. The result will shock you, or should I say burn you out? That was terrible. But anyways, my hypothesis is that this is going to pop much sooner than this, mostly because of transference of heat. This balloon is filled with a gas, having it easier or more space for heat to spread in a quicker manner, whereas this is filled with water, and water has a very high heat retention. Rubber itself does absorb heat very well, but just in here it's going to heat up a lot quicker than, say, water. It's very difficult to heat up water. It takes a much longer time. So the molecules in the air will push against each other because the heat and the fire is making the molecules collide, and the molecules will move faster. That's basically what I'm trying to say. And it will cause more pressure on this weak spot, and the mass of the air inside of it will heat up as it takes up more space, causing it to pop. Moving on to the water balloon, when we put water in a balloon and we put a fire under it, it's not going to pop. This is because even when touching the balloon directly with the flame, we know that water has a greater heat capacity. The water will absorb the heat and try to warm it before allowing the transference of the balloon to actually pop within itself. The heat from the water is going to rise because of general physics, but the heat will go up to the top of the balloon and not stay at the bottom. The heat will form around the entire balloon, whereas this one, all the heat's going to come here and it's going to pop event, like right there. The latex itself is mostly unharmed, and when you brush it off, you should be able to see the same strength. In a real-world context, this is the reasoning why water, out of all the compounds possible, is used to put out fires, and ultimately proves here that water controls heat better than normal space filled with air itself. So without further ado, I'm going to be testing that this balloon will pop at a much quicker time than this balloon, being the air, being the water. Okay? So let's get to it. I hope I'm safe. Here we go. Oh! It didn't pop per se. If you heard the noise it made there. It heated up, it got really hot, I can smell the rubber off of it. But it didn't necessarily pop. It just broke a hole. I wish I had a timer going. That was probably about 6 seconds, I'd say, give or take, for it to actually lose its form and air escape from outside of it. Now let's check the water balloon. I'll be timing it in my head. Oh, it's starting to smoke a little bit. But as you can see, even with the blue flame directly on it, it is not popping, no matter what. It's still really smoky. And it looks like a tiny bit of water. Nope, still nothing yet. We'll see if it even pops. I believe water has such a high heat capacity where this thing will take a long time to actually pop or lose its form, because the water itself is keeping it from popping. We'll hold it here for a little longer. Yeah. The other one took seconds, whereas this is probably going to take a couple minutes. But as you can see, it's really transferring the heat very well, like throughout the whole entire thing. It's hot to the touch, and you can see here the bottom of it is completely black compared. You can even pick it up on the camera. This is totally different, but it's because water molecules have a greater time absorbing heat and not having it explode, where this has a very low heat capacity and will blow up very soon. But thank you for checking out this week's science experiment. I'll see you next week.